Hey everybody, we're back to look at the handout from section 5.2, which is about the binomial probability distribution. Okay, recall that if something is binomial, it has to satisfy the Bernoulli trials. They are Bernoulli trials, meaning that there are a fixed number of trials, n, right there, fixed number of trials for n. There can only be two possible outcomes. So two things could happen, like flipping a coin, or something does happen or it doesn't happen. The probability of success in any trial is constant, meaning the probability that the thing you're counting happens is the same every single trial. And then lastly, the trials have to be independent. Most often, being independent and having the probabilities remain the same. These last two kind of go together. And being independent is often satisfied by just saying we randomly select things. If we say things are randomly selected, then they're assumed to be independent. The notations we use for the formulas are n is the fixed number of trials. We'll use that even in StatCrunch. And p is the probability that the thing that you're counting happens in any single trial. And so then its complement, 1 minus p, is the probability that it doesn't happen in any one single trial. And then x is the thing that we're counting. We want to see how many times does it count. All right, we have this formula which we can use, but we're not required to. But we can if we wish. In this case, we're just going to jump over and use StatCrunch. So I just wanted to show you what these handouts would be, what I would have you be doing in class. So if we assume that n equals 10 and p equals 0.75 in a binomial experiment, I want to find the probability that x is equal to 8. And then I want to find the probability that x is at most 8 or at most 5. And then the probability that x is 8 or more. Okay, no matter how we look at it, we need to look at StatCrunch. Okay, so n is 10, p is 0.75. So I'll come over here to StatCrunch and go to Calculators, Binomial, and n is 10, that's good, and p is equal to 0.75. And we wanted to find the probability that x was equal to 8. So I'll change this to equals. Okay, so we're going to put in x equals 8, because we want all the probabilities equal, and 8, and compute. And there it goes. Now you can see that if x equals 8, there's this red bar right there. That's the highest probability. That's the most likely thing that could happen. It's a slightly skewed distribution, slightly skewed to the left, but not terribly badly. Okay, so that's the probability that x is equal to 8. We were also asked to find the probability that x is at most 5. So that would mean we want to change the 8 to a 5 on the distribution. And being at most 5 would mean, well, it couldn't be any bigger than 5. It couldn't be 6, for example. If it's at most 5, it can't be 6. So that must mean it is less than or equal to 5. So again, you can see that these little bars are red, and these represent the probabilities. So the first one is about 0.05 or a little bit higher than that maybe. And the probability altogether is 0.0781. Okay, so it's 0.0781 is the probability that x is at most 5. The last thing we're supposed to find out is the probability that x is 8 or more. So I'll go back, change the 5 back to an 8. An 8 or more means it could be 8, or it could be 9, or it could be 10. So we need to change the direction here to x could be greater than or equal to 8. So here's the 8, here's the 9, and here's the 10, and you can see they're on the right side. One of the little tricks that I usually say in class is, if you look at this inequality, x is bigger than 8, and the arrow is pointing to the right. So you can see what's red there, and the x arrow is pointing off to the right. Okay, and that probability is 0.52559 or 0.52556. Okay. Okay, now let's flip back over to the problems. What's the next problem? Okay, very similar. Assuming that n equals 25 and the probability of success in any one trial is 0.15 in a binomial experiment, find the probability that x is 7 and it's 7 or less, or it's at least 10. Okay, so let's go back and put in n equals 25 and p equals 0.15. Okay, so n equals 25 and p is equal to 0.15. Okay, and now we're supposed to find the probability that x is equal to 7, 7 or less, and at least 10. All right, so 7 equals 7. The probability that it's equal to 7 is 0.044. That's not very likely. Okay, the second question is find the probability that x is 7 or less. So let's check 7 or less. Come back over, we still have 25 and 0.15. I'm going to type in a 7, and 7 or less would mean less than or equal to. It could be 7, or it could be less than 7. You see there's a lot of red there, and the probability is 0.97. So it's pretty close to 1, which makes it pretty likely. Okay, let's check the third problem. Find the probability that x is at least 10. Okay, if you're going to be at least 10, that would mean you have to be compared to 10. X could be 10, or at least 10 could be 11 or 12, anything bigger. So now we compute, and it's 0.002. It's highly unlikely. You can barely see. You might be able to see these two dots right here are slightly pinkish. They're supposed to be red. Okay. Back over here. We used the Steph Curry example in one of the other videos, but I'll use that one again. Steph Curry makes 91% of his free throws. Assume he takes 20 free throws. Let's let x equal the number of free throws that he makes. So first of all, why is this a binomial experiment? Well, if you make a shot at a free throw, you're either going to make it or miss it. So there's two possible outcomes. In this case, he's going to take 20 free throws, so that's 20. That's a fixed number of trials. We can assume that his free throws are independent of each other, because if he makes one, it doesn't make it any more or less likely the next one will be made or missed. And the probability is assumed to be 91% throughout. It's always the same number. Okay, so that explains why it's a binomial experiment. Part B then says, what's the probability that he makes 18 or more free throws? And then what's the probability that he makes 19 or 20 free throws? Okay, so when I go over to StatCrunch, the important thing here is this 91%, I can't write it as 91. It's got to be 0.91. Okay, so we'll put in 20 for the number of attempts, and 0.91 for the probability, and being greater than or equal to 18 is 0.7334. So 0.7334. So making 18 or more out of 20 is very highly probable, 0.7334. Let's go back and look. So 18 or more free throws, that's 0.7334. Find the probability that he makes 19 or 20 free throws. Okay, 19 or 20. We just need to change this to, we could change this to greater than 18. It's 0.45. Or it could be greater than or equal to 19. Also 0.45. Okay, those mean the same thing. All right, so that's how you compute binomial probability using StatCrunch. If you have an app for your phone, you are welcome to use that as well. All right. Thanks a lot. I hope this helped, and I'll talk to you soon. Bye.